Good morning, our students, and welcome to this moment's class. Today, we want to continue our discussion on time series models. Particularly, we will be looking at the autoregressive model of order 2. This is because in some of our previous classes, we already had looked at the introduction to the autoregressive models. We equally have had a detailed discussion on autoregressive model of order 1. So this moment, we want to look at in details the autoregressive model of order 2. And we are going to have guidelines or items under which we are going to have this discussion. These are. And these headings or guidelines are: 1, we are going to look at the model of AR of order 2 model. So we are going to look at what we call the what? The model. Number 1, we look at the model of AR of order 2 model. Number 2, we are going to look at the mean of AR of order 2 model. We are going to look at what we call the variance of AR of order 2 model. We are going to look at what we call the autocovariance function. Autocovariance function of AR of order 2 model. We look at the autocorrelation function of AR of order 2 model. Then we now look at number 6, stationary condition. The stationary condition of AR of order 2 models. So we begin with the first one, talking about the model of AR of order 2 model. How is the model written? The model of AR of order 2 is written this way: that y of t is given as phi naught plus phi 1 y of t minus 1 plus phi 2 y of t minus 2 plus a of t, such that a of t follows normal distribution with mean 0 and constant variance sigma squared of what? Of a. This is how to write the model of AR of order 2 model. So the next thing we are going to look at is, what is the explanation of each of the term in this model? What is y of t? Of course, y of t equals the value of the series at time t. Value of the series at time t. What, of course, is our phi naught? Our phi naught is the mean constant in a model. Mean constant in the model. Then what is our phi 1? Phi 1, of course, is the weight that this previous value of the series at time t minus y 1, written as y of t minus 1, have on y of what? Of t. That is the weight or the contribution of this previous series y of t minus 1 on this current observation y of what? Of t. The same thing applies with phi 2. Phi 2 is the weight that this previous observation y of t minus 2 have on this y of t. What is our y of t minus 1? It is the previous observation of the series at time t minus 1. What is y of t minus 2? It is the previous value of the series at time t minus what? 2. Then what is our a of t? The white noise term in the what? In the model. So this is the explanation of the terms what in the model. So the next thing here is, looking at this, we can see that this is actually a regression model where the current value of the series is a regress on the two previous values of what? Of the series, or on the previous values of the what? Of the series at time t minus 1 and time t minus what? 2, and then the white noise at the current time. So that is actually how to write and explain the model of AR of order 2. So we now quickly go over and then look at what we call the mean of AR of order 2. So you permit me to clean this. If you want to look at the mean of AR of order 2 model, of course, it is going to be that we are going to take the expectation of both sides of what? Of the equation. We take the expectation of both sides of what? Of the equation, which of course is going to be E of y of t is given as what? E of phi naught plus phi 1 E of y of t minus 1 plus what? Phi what? 2 E of y of t minus what? 2 plus E of what? A of t. Okay? What I have just done now is to take the expected value of both sides of what? Of the model, and of course, the expected value of this y of t is given as what? Mu. B is equals to. Expected value of a constant is a constant, phi naught. Here becomes what? Phi 1. Let me remind us that a stationary time series model has its mean, its variance, and its autocovariance constant over time. By implication, the mean of the series at yt or at time t is same thing as the mean of the series at t minus 1, which is the same thing as t minus what? 2. So in that case, here equally becomes what we call mu plus phi 2 of what? Mu plus. We already had said that this error term follows normal with mean 0. So here becomes what? 0. So I bring all the terms that contains mu to the left, and I have what we call mu minus phi 1 mu minus phi 2 mu is given as what? Phi naught. I factor out my mu into 1 minus phi 1 minus phi was 2, close it, this is equals to phi naught. Making mu to stand alone, therefore, my mu is given as what? Phi naught all over 1 minus phi 1 minus phi what? 2. And this becomes the mean of the autoregressive model of order 2. Okay? Situation that when we are given something like this, if we are given that y of t is given as 4.5 plus 0.5 y of t minus 1 minus 0.2 of y of t minus what? 2 plus a of t. We might be asked to find the mean of this what? Model. So what we are going to do is to quickly remember that the mean of the autoregressive model of order 2 is given as this. Here is the phi naught is the constant, which is 4.5. Phi 1 of course is what? Is 0.5, and then phi 2 is minus 0.2. So the moment you substitute this value into here, you'll be able to have your answer there. So that is how to arrive at the mean of the autoregressive model of order 2. So let us now look at now the variance of autoregressive model of order 2. The variance. So you permit me to clean here. If you want to look at the variance of the autoregressive model of order 2, you are to take the variance of both sides. And because the variance of a constant is 0, we are going to skip this phi naught and make use of the other one. So the model equally can be written as that this is y of t is given as phi 1 y of t minus 1 plus phi 2 y of t minus 2 plus error term, where this error term still satisfies that particular condition. What are we going to do? What we are now going to do is to take the variance of what of both sides. And by taking the variance of both sides, we first of all recall for ourselves that when you want to take the variance of sum of random variables like, you have var of x plus what y. It is given as var of x plus var of what y plus 2 covariance of x comma y. That is the rule. By implication, what we have just done here is you take the variance of the individual random variables before you now talk about the pairs, which is the covariance of the pairs of what of the random variable. Assuming I had x plus y plus z, I could have taken the variance of x plus the variance of y plus the variance of z. I will now say plus the 2 covariance of x and y plus 2 covariance of x and z plus 2 covariance of y and z. By that, I've considered all the pairs there. So I'm going to use this ideology now to take the variance of this AR of order 2. And that will make me to have that v of y of t is given as, when you want to take a variance of a constant, it gets squared. So you have phi 1 all squared v of y of t minus 1 plus. Here is phi 2 all squared v of y of t minus 1 2 plus. You have v of what a of what of t. I am done taking the variance of the individual terms there. It is for me now to begin to consider the covariance of what of the various pairs. That is this to this, this to this, and this to that. So I now have, I'm going to take the covariance of this and this. So I have my what 2, but because I have the constant phi 1 and phi 2, I will bring them out. Phi 1, phi 2, covariance of y of t minus 1, comma, y of t minus what 2, close it, plus. When I take this and this, you find out that when you take the covariance, let me write this, covariance of ai, comma aj is equals to 0 for I not equal to what? J. Okay? So when you are considering the white noise at different time lag, they are uncorrelated, and as such, their covariance is what is 0. When you consider this pair and this pair, and you express this y of t minus 1, there is no term in y of t minus 1 that will contain a of t. And by implication, the covariance of this quantity and this quantity will give us what? 0. The same thing applies here. If you take this and this, there is no term in y of t minus 2 when it is expressed that contains a of t, so its covariance is equally going to give me what? 0. So every quantity here is now going to give me 0. So what am I going to do? I will now consider this alone. So this is going to be that my v of y of t is given as, we have phi 1 all squared, sigma squared of what? Y, because this is variance, plus phi 2 all squared, sigma squared of what? Of y, plus. Here becomes what? Sigma squared of what? A, plus. We have what? 2 phi 1 phi 2. The covariance of y at t minus 1 and y at t minus 2 is what we call gamma 1. That is autocovariance at lag 1. Why did I have sigma squared of y here, sigma squared of y here, and I have sigma squared of a here? This sigma squared of y here stands for the variance of the series at time t minus 1. It equally stands, this sigma squared of y here stands for the variance of the series at t minus 2. Bearing in mind that the variance of a stationary model is constant over time. So its value at t minus 1 is the same thing as its value at t minus 2. However, here we are talking about the variance of the error term. And ab initio, the variance of error term is given as sigma squared of a. That's why I have sigma squared of a here. So here is my what? My 25152, 25152 covariance of the series at t minus 1 and at t minus 2 is what we call gamma 1. That is covariance at lag 1. The next thing we are going to tell ourselves is this. We can decide now to bring everything that contains sigma squared of y to the what? To the left. And in that case, you are going to have this. You have, of course, this one equally is sigma squared of y. So you have sigma squared of what? Y minus. This one comes over here, phi 1 all squared, sigma squared of y minus phi 2 all squared, phi 2 all squared, sigma squared of y is equals. Then you have sigma squared of a plus 2 phi 1 phi 2 gamma 1. Gamma 1. Then you factor your sigma squared of y. So you have that your sigma squared of what? Y, you open a bracket. Here is 1 minus phi 1 all squared minus phi 2 all squared, close it, is given as sigma squared of what? A plus 2 phi 1 phi 2 gamma 1. And making this your sigma squared y to stand alone, you have sigma squared of what? Y is given as, here becomes what? Sigma squared of what? Of A plus 2 phi 1 phi 2 gamma 1 all over 1 minus phi 1 all squared minus phi 2 all squared. So one can require you to show that the variance of AR of order 2 model can be given as this. However, there are other variations that you can see in a textbook still talking about the variance of AR of order 2 model. And of course, I am going to show that here in case you run into one. Permit me to clean here. Permit me to clean this place. When you talk about, there is a relationship between the autocovariance and autocorrelation. The autocovariance or the autocorrelation at lag k is written as rho k. And it is expressed as this equals what? Gamma what? K all over gamma 0. This is the relationship between the autocorrelation and autocovariance. That the ratio of autocovariance at lag k to autocovariance at what? At lag 0 will give you the autocorrelation at lag what? K. By implication, here all over 1, this time this will give me that gamma k is given as rho what? K, then we have what? Gamma 0. But here we are talking about what? Gamma 1. So I can decide now to say, therefore, that my gamma 1 is going to be rho 1 gamma 0. That is, here is k, here is k. I am saying when k becomes 1, which is of course what we have here, we have that gamma 1 is equal to rho 1 gamma what? 0. So I can easily come here and claim that, therefore, that my sigma squared of y is given as, here I have what we call sigma squared of what? A plus. I have what? 2 phi 1 phi 2. Instead of writing this gamma 1, I'll write what? Rho 1 gamma 0 all over 1 minus phi 1 all squared minus phi 2 all squared. One can equally ask you to show that the variance of AR of order 2 model can be given as this. Okay? I also want to tell you something. That this gamma 0, of course, is the variance of what? Of the model. And if this gamma 0 is the variance of what? Of this model, somebody can say that this gamma 0, gamma 1 here, that this gamma 1 is given as rho 1 sigma squared of what? Of y. And in that case, somebody can easily now come here, or somebody can easily come here, look at where I am now here. So permit me to clean here, you have seen what I showed here, and show you something from here. So somebody can then come here, in place of this, substitute this, and the person will be able to have here that this thing becomes, permit me, this is now going to be here that this my Vt, which is sigma squared of y, is equals to phi 1 all squared, sigma squared of y, plus phi 2 all squared, sigma squared of y, plus sigma squared of what? A, plus what? 2 phi 1 phi 2 rho 1 sigma squared of what? Y. So that in that case, on bringing everything that contains sigma squared of y, this one is now among. And we'll be able to have that sigma squared of y minus phi 1 squared sigma squared of y minus phi 2 squared sigma squared of y minus 2 phi 1 phi 2 rho 1 sigma squared of y is equals to sigma squared of what? A. And factoring your sigma squared of y, you'll be able to have therefore that sigma squared of what? Y is given as sigma squared of what? A all over. Here become 1 minus phi 1 all squared minus phi 2 all squared minus you have 2 phi 1 phi what? 2 rho 1 and rho 1. Then you have this thing. So somebody can equally ask you to show that the variance of AR of order 2 model can be given as this. So whichever way they ask you to show that, you'll be able to show it. Okay? So you permit me to clean this while we now talk about the next thing there. Remember that the moment you have the value of rho 1, you can equally substitute here. You can equally substitute the moment you have the value of rho 1. You can equally substitute it here. So we want to quickly look at what we call the autocovariance. The autocovariance. The autocovariance, of course, we are still talking about our y of t is given as, we have a phi 1 of this. So here becomes our sigma squared of what? Of A. When we talk about the autocovariance, we are going to multiply both sides of what? Of the equation with y of t minus k, and then take expectation. So by multiplying with y of t minus k, I have y of t for this one multiplied by y of t minus k is equals. Here becomes phi 1 y of t minus k minus 1 here multiplied by y of t minus k. Then we say plus. Here is my phi what? 2 y of t minus 2 multiplied by y of t minus k. Then plus. Here becomes what? A of t multiplied by y of t minus what? K. Okay? So what we are going to do now is to take the expected value, and taking the expected value, what I'm going to have is E of what? Y of t multiplied by y of t minus k is given as phi 1 E of y of t minus 1 multiplied by y of t minus k plus phi what 2 e of y of t minus 2 multiplied by y of t minus k plus we have what we call e of a of t multiplied by y of t minus k. Okay. The only thing that can make people now to have a of t here and equally have a of t from this expression is when k is equals to 0. That is the only condition. If a is equals to 0, y of t becomes what we have here, and then we'll be able to have this a of t. Okay? And then if this a of t comes inside now, it becomes a different value. But this time around, we are talking about when k is equals to 1, when k is equals to 2, what happens to this expression? When k is equals to 1, when k is equals to 2, what we are going to do is this. To come, here is what we call gamma k, autocovariance at lag k. This is equals to, here it becomes what we call phi 1. Here is autocovariance at lag k minus 1. So we have gamma k minus 1 plus. Here becomes what we call phi 2. Here becomes what we call gamma k minus what 2. So this is for k greater than or equal to 1. For k greater than or equal to what? 1. So this is how to get what we call the autocovariance. How do we get the autocorrelation from this? It is simple. Like I earlier had said, the autocorrelation is given as that rho k is equals to what? Gamma k all over gamma 0. So here now, if I want to express it that way, I will say therefore, here now, dividing all two with gamma 0, I have that gamma k all over gamma 0 is equals to phi 1 gamma k minus 1 all over gamma 0 plus phi what 2 gamma k minus 2 all over what? Gamma 0. So what are we going to do here? Here becomes what we call our rho k. This is equals to, here becomes what we call phi 1 rho k minus 1 plus phi what 2 rho k minus what 2. This condition is equally for k greater than or equal to what? 1. When at least if k becomes 0, see it from this expression why we are not paying attention here for when k is equals to 0. Because when k is equals to 0 here, what you are going to have is that rho 0 is equals to gamma 0 all over gamma 0, which is equals to 1. And that's the reason why they say that the autocorrelation at lag 0 is equals to 1. Okay? So if somebody asks you to obtain the autocovariance of AR of order 2 for k greater than or equals to 1, you arrive at this. If somebody says obtain the autocorrelation function of AR of order 2 for k greater than or equal to 1, it is given as this. Then, of course, when someone says for k is equals to 0, you can either explain to the person this way or you come here and say that when k becomes 0, here is going to be gamma 0, here is going to be 0 minus 1, which is same thing like saying gamma 1. Here is going to be 0 minus this, which is same thing like saying gamma 2. So that is how to show this particular thing. Okay? So you permit me now to clean the board. What I said here is that if k becomes what? 0, you have gamma 0 is equals to, when you come here, you have what? Phi 1 gamma. 0 minus 1 is minus 1. The autocovariance at minus 1 is same thing as autocovariance as at 1. At lag minus 1 at lag 1 is the same thing. So I can say at 1 plus. You have phi what? 2. Here becomes what? 0 minus 2, which is the same thing as what? Gamma 2. So if they are talking about for k equals to 0, this is what you are going to have in terms of what? The autocovariance. But in terms of the autocorrelation, you are going to have this into a 1. So you permit me now to clean here, and then we now talk about what we call the invertibility condition. The invertibility condition. Sorry, the stationarity condition. Stationarity condition. Okay. For AR of order 2 model to be said to be stationary, its characteristics equation must lie within a unit what? Circle. Okay? It must lie within what? A unit circle. That's what we talk about the auto the stationary condition. Okay? Or what we say must lie outside the unit circle. Sorry. Must lie outside a unit circle. Okay? So in that case, we are going to talk, let me talk about the stationarity condition in terms of what? Of the parameters. In terms of what? Of the parameters. That AR of order 2 model is said to be stationary if we have that absolute value of phi 2, absolute value of what? Phi what? 2 must be less than 1. That is for number 1. Number 2, we say that phi 2 minus phi 1 must be less than 1. Then number 3, we have that phi what? 2 plus phi 1 must be less than 1. So if the parameters of the AR of order 2 model satisfy these conditions, one can say that the AR of order 2 model in question is stationary. Okay? Then you can equally now talk about what we call the Euler-Walker equation of AR of order 2. The Euler-Walker equation. So you permit me now to clean here and then show you about the Euler-Walker equation. If you talk about the Euler-Walker equation, equations. To obtain the Euler-Walker equations, what you need to do is to write your formula for the autoregressive autocorrelation function of AR of order 2, which of course is written as, like we earlier had shown, that rho what k is given as phi 1 rho what k minus 1 plus phi what 2 rho k minus what 2. We now say for k greater than or equal to what? 1. So we are going to obtain the expression for this at k equals to 1 and obtain it at k equals to 2. And whatever thing we have as the answer is actually what we call the Euler-Walker equations. So see what we are going to do. When k becomes 1 here, what we have here becomes rho 1 equals phi 1. 1 minus 1 will give us rho 0 plus. Here is what? Phi what? 2. 1 minus 2 will give us minus 1, which is just like writing rho 1 because the autocorrelation at lag minus 1 and at lag 1 are the same thing. So here becomes what? Rho 1. But we recall for ourselves that we earlier had shown that the autocorrelation at lag 0 is equals to 1. So here is equals to 1. So this equation implies that rho 1 is equals to what? Phi 1 then plus what? Phi what? 2 rho 1. So this implies this. Okay? And we call this one, of course, our equation 1. We have gotten our equation 1. And from this our equation 1, we can easily know what the value of the rho 1 is going to be. Having known that the value at rho 0 is what? Is 1. If you bring this in over here, you have that rho 1 minus what? Phi what? 2 rho 1 is equals to phi 1. Then you factor out your rho 1 into 1 minus phi what? 2 is equals to what? Phi 1. And then your rho 1 now is given as what? Phi 1 all over 1 minus what? Phi 2. This is also one of the reasons why we have variation in the formula of the variance of AR of order 2 models. Because you do remember that the formula which we gave for the variance of AR of order 2 model contained what? Row 1. And one can easily go there and in place of this row 1, substitute this. And you now have equally another variation for that. Okay? So we now quickly now talk about when k becomes what? 2. So you permit me to clean here and we talk about when k becomes what? 2. So when k becomes 2, what we are going to have here is that row what? 2 is given as phi 1, row 1 plus phi 2, row 0. Because here is 2, here is 2 minus 1, 1, here is phi 2. So that this implies that row what? 2 is given as phi 1, row 1 plus phi what? 2. Reason being that this is of course what? 0. We call this one our equation what? 2. Our equation 2. Okay? So, and of course, from this expression now, we can easily know what our row 2 is going to be. Bearing in mind that our row 1 was, we say, but our row 1 is equal to phi 1 all over 1 minus what? Phi 2, I guess. So if you bring it in here, you have therefore that your row 2 will be given as phi 1, open the bracket, phi 1 again all over 1 minus phi 1, close the bracket, plus what? Phi 2. When this goes into this, you have phi 1 all squared all over 1 minus what? Phi, this is phi 2 plus what? Phi 2. So you have something like this for the value of your row 2. So the moment you know the value of the parameters, you can easily get the values of what? Of the row. Assuming someone says, gives you something like this, assuming somebody says y of t is given as, let me say 4.5 plus 0.5 y of t minus 1 minus 0.35 y of t minus what? 2 plus a of t. And the person begins to ask you to use this expression and get what? Row 1, use it to get what? Row 2. Use it to get what? Row 0. You just know that row 0 is autocorrelation at like 0, which is equal to what? 1. So if you come here, you know the value of your phi 1, you know the value of your phi 2 from this, you'll be able to know what you are talking about here. Here is your what? Your row 2, you can know this value, you get it from here, you put, you'll be able to get what the value is, straightforward. Okay? So you permit me now to clean here and show you how at times these two equations, which we call the Walker equations, can be expressed in form of what? Of a matrix. So you permit me to clean here. So you can easily come here, this particular place now, and you have something like this. You have that your row 1, which is this one, then row what? 2, this way and this way is given as, you open a bracket, here becomes what you call your what? Your 1, row 1, 1, and your row what? Your row 1 here, sorry, and your 1. You close the bracket, then you have something like this. You have what you call phi 1 and phi 2. You close it. Then we check whether if we open this, we can get this. When this multiplies this, you have this. When this multiplies this. When this multiplies this, you have this. When this multiplies this, you have this. When this multiplies this, you have this. And when this multiplies this, you have this. So these equations and these equations are the same thing. This one is expressed in form of a matrix, but this one is just expressed in form of either simultaneous linear equations. So having this, it implies that somebody can easily use this expression to look for phi 1 and phi 2, knowing the value of this. If you know the value of row 1 and row 2, you can be asked to find the value of what? Phi 1 and phi 2. You just need to put that value of row 1 here, put the value of row 1 here, put the value of row 1 here, put the value of row 1 here, make this into some sort of formula by dividing both sides with this quantity, which when it comes here becomes inverse. Then use it now to evaluate whatever thing you have here, and that becomes the value of what? Phi 1 and phi 2. So somebody can easily give you the values of row 1 and row 2 and ask you that that value of row 1 and row 2 are coming from AR of order 2 model. That if you use those values now to find the values of the parameters of the AR of order 2 model and equally write the equation. When questions like that now comes up now, this is the approach you are going to use to go about it. Please, so that the time of this video will not be too large, permits us to stop by now. And of course, when you listen to our class and you're having challenges, please do well to reach out to us in the comment sections, either in a way to improve our classes or in whatever way you are confused in our class that you would want us now to give explanations to. Thank you very much. Remember to subscribe to our YouTube channels as we are committed to bring a positive change to the understanding you have about math and statistics. Thank you. Stay tuned for our next class.